Audience, thank you so much for tuning into the 3D Print Authority podcast. This is where we come together to have a transparent and no BS conversation about the world of 3D printing and technology. Joining me today is Sergey. You are the, I'm going to say, founder, inventor of Iro3D. And I was super excited to connect with you because you have such a unique take on metal 3D printing that I don't see anybody else doing. And so I think there's a lot that I can learn and that a lot that the audience can learn from kind of your experience. Could you go ahead and kick things off just to introduce yourself to the audience?
Sure. My name is Sergey Singov. I'm an inventor of the Iro3D selective powder deposition 3D printing method.
Awesome. Thank you. And the company's Iro3D selective powder deposition. When did you first get
Forger 3D?
I'm sorry.
Company is Forger 3D, but
Forger
most of
3D.
the things Forger 3D. Most of the things are on the Iro3D website. Forger 3D has like pretty much nothing on the website.
Okay, gotcha. So that explains my confusion. So there's a couple different names and websites.
You know what? Let's just call it Iro3D. That's fine.
Fair enough. When did you first get started on this project and this 3D printing method?
Well, at first, like a while ago, I saw a plastic 3D printer in a makerspace.
Okay.
I think it was Darwin 1 or something. And it wasn't very good. So it was like printing with a very thick nozzle. It's like 0.8 millimeter, or maybe even like 1 millimeter.
Okay.
And the layer didn't adhere to each other. So it looks like a bunch of like spaghetti, which didn't stick to each other well, and say, well, we need to tune it, but usually it's better. And they had like big problem with overhangs. Well, because of the technology was not as well tuned as it is today.
Sure.
But I started to think, how can I improve this adhesion? So I had this idea of having like a rotating bed, so the nozzle would always print vertically without having to have any overhangs.
Okay.
So that was like the first idea, didn't quite went there. But in 2015, I was laid off work.
Okay.
And I was thinking, what I'm going to do next. And I thought, I have this idea. Why don't I like start working it? And actually, the first idea didn't work. But then I had another one. So finally, I got to this one. So this one seems to be working. It's still very far from being done.
Okay.
I think we're like barely scratched the surface. There will be a lot more improvements. Not just by me, but like by other people, and not just in this technology. Like in any technology related to 3D printing, I think we'll have lots of maybe new technologies. So it's like 3D printing as a technology is very young. Like if you compare it to like math or physics, it's just like newborn.
Definitely. So in 2015, what were you doing? Kind of what was your background before you decided to try to pursue this idea?
I was a software engineer.
Okay.
I was writing programs for Android.
Okay. Very cool.
But I did like to tinker with the mechanics and electronics for quite a while. So I knew a good deal about mechanics and electronics. And after I had this idea, I also started to learn chemistry.
Okay.
So now I know like some bit of chemistry and metallurgy.
Yeah, that was my first thought. Is I'm usually so jealous of programmers because that's just a skill set that I don't have as a mechanical engineer. But then to actually make a 3D printer, especially a metal printer, you need to know a little bit of a lot of different areas.
Yes, but when you say like you don't know programming, for example, like I didn't know chemistry, I didn't know metallurgy, I knew nothing about metallurgy.
Okay.
So the benefit of living in a modern world is that you can learn pretty much anything for free.
Okay.
When people say like, oh, education is so expensive. No, the paper piece of paper is expensive. Education is free. You can get it online.
Is that what you did? Did you just like go to YouTube and start looking for things?
I started with Khan Academy.
Okay.
So I took a chemistry course on Khan Academy. Then I took 2 chemistry courses from Coursera.
Okay.
And then I took another course. Well, I took half of it on YouTube from MIT.
Okay.
It was a very good course, but I didn't quite finish it. By that time, I already had the technology mostly working.
Sure. So what was your first steps? I'm trying to think back. 2015 was such also a young time in 3D printing. People were excited about it, but like the Ender 3s and the Prusas, those weren't really out there to kind of form a foundation for people.
Well, Prusa was out there.
Okay.
Prusa was out even in 2014.
Okay.
So I bought the first 3D printer I bought was a Prusa clone.
Okay.
It wasn't very good, but it was kind of working.
Gotcha.
So what was the first step? It's very hard to say because it's not just one step. It's like lots of incremental steps until you get something. And even like this something, like when I printed the first metal part, it looked like nothing what we have today. It was like, oh, this tiny thing is 3D printed. They say, yeah, okay. So, and even what we have like right now, it's still not quite there yet.
Okay.
So, well, not quite there for most people. Like for most markets, it's still not quite there. You can still print something like cool looking and so on my channel, but there is still a good amount of work we need to do.
Okay. So for people that aren't familiar, can you kind of just walk us through how your process works? So say we start with a 3D file. What's the first step that we're going to take?
Well, you start a 3D file. You start with a 3D file and the 3D printer. The Model G is behind me.
Okay.
I have 2 Model Cs in the other room. You put it in the slicer.
Okay.
Slicer slices it, converts it to the G code.
Okay.
And sends it to the printer. But before you before you can print something with the printer, you need to put the powders. So there are powder containers. So you need to put sand and metal. So basically, you need to have 2 types of powders.
Okay.
Support powder and build powder. So you deposit build and support powder selectively in a crucible. So you fill the crucible all the way to the top. So there is like no empty space, but some of the volume is filled with build powder, some of the volume is filled with support powder.
Okay.
And the build powder should be exposed to the top, generally.
Okay.
Then you place a piece of infill metal on top and bake it in a kiln.
Okay.
Infill metal melts and soaks the metal powder.
Okay.
It doesn't soak the sand because sand is not wettable by the molten infill metal.
Okay.
So that's it in a nutshell. There are many process variants. Like for example, instead of like placing a chunk of the infill metal on top of the having a contact with the powder, you can have a like for example zinc. You can take a piece of zinc and put it near, and bake it, and you have to close the crucible in some cases. So you close the crucible, zinc starts to evaporate. At about 850 degrees, it evaporates quite fast.
Okay.
So it evaporates and the vapor is like everywhere in the crucible. And whenever the vapor of zinc touches copper kind of like absorbs it.
Okay.
And it becomes a solid object. Actually, do you want me to bring one?
Yeah, that would be great if you have one sitting around.
So this is the latest.
Okay.
Print.
That looks really good
Uh,
for anyone that's just listening and doesn't have the video in front of them. Sergey's holding up what looks like a bronze chess piece. It's got some really cool spirals on the outside, and it looks really clean from what I was imagining as you're describing the process.
yeah. On the sides, whatever you see on the sides, it's a virgin surface, untouched.
Okay.
On the top here, I polished it.
Okay.
People were asking me, like, how does it look like? It doesn't look like metal. And I didn't
Right.
do this. If I do this,
Yeah.
you can hear that it rings. But in the video, I didn't do it. So people are like, oh, what is it? Is it metal? But if you polish it, not sure how you see it.
Yeah.
You,
So
you
I
can
can
feel that
see
it's metal.
it's a shiny, almost not like a mirror finish by any means, but it's a shiny reflective surface that's been polished
Yeah.
on the bottom of the chess piece.
Yeah.
If someone is listening and they aren't familiar with how the body of the chess piece looks, it looks just like a cast metal part. Like if you had a sand casting or maybe a die cast part, looks really similar.
Actually, it would be very hard to cast this shape.
Okay.
Maybe like close to impossible because this geometry is like almost uncastable. Well, if you can, it would be very hard.
Yeah, with the spirals that it has a shape that even if you did cast it, you'd have to do a lot of digging to get out kind of the investment material.
And actually, I have an object that's practically uncastable.
Okay.
I'm not sure if I can find it. Maybe I can. If you do, you want me to dig and find it?
Let's keep talking for now.
Okay. So the other one has a spiral. It has a spiral hole.
Yes.
You cannot cast it.
Right.
I don't think so. Maybe someone can. I don't think so.
If someone's watching and they are a casting expert, please let us know whether or not the chess piece that we were just showing on screen is castable, because to my knowledge too, it's not possible.
Chess piece might be castable. It might be castable, but within Western question. But the piece with the spiral hole, I think this one wouldn't be. But I would like to hear what people say.
Definitely. So what's interesting to me about your process is that the metal isn't sintered, which is much different from a lot of, if not every other metal 3D printing process. What's going on there?
Yes. So there are several ways to do it. The first method I thought about would be infilling with the liquid metal.
Okay.
And I think it's, well, pretty much the best method because you have no sintering and there will be no shape distortion and no shrinkage.
Right.
Because the metal powder, it doesn't melt. It always stays solid.
Okay.
So it holds the shape. There is some very small distortion due to the thermal expansion.
Okay.
When things expand, they expand unevenly, and so you have some small distortion, but generally it's very small. It's like much smaller than what you have with sintering.
Okay.
So that's the advantage of this method. You preserve the shape. You don't need to correct it in the software to account for shrinkage, because the shrinkage is also non-uniform. So whenever you have shrinkage, you have distortion. So this method does not have this problem. I think this is one of the main advantages. But you still can use shrinkage. You can still use sintering, and you'll have shrinkage with the SPD process.
Okay.
Like, for example, I printed glass. I can also bring and show it. There, you don't infill anything. You just take glass powder.
Okay.
As a build powder. You take sand as the support powder, and you sinter it. And for artistic figures, it's fine. Well, it gets a little bit smaller and a little bit distortion, but you don't see it because on artistic figures, it doesn't really matter that much.
Okay.
So in the third one, I already mentioned before with the vapor infill. You can infill it with vapor. And you can play with the parameters. You can maybe choose the parameters such that it would be porous, but you'll have like no shape distortion. So I don't know. I haven't done an in-depth analysis of this method yet, so this is a fairly new method.
Okay.
So it might have some advantages, maybe like simplicity, because you don't need to have a delay in fill, because, well, delay in fill is another thing. For some metals,
Okay.
you would need to have delay in fill. Well, I can go into details, but that will be maybe like too technical. It's on the info is on my website. So if you go to the iro3d.com and see the frequently asked questions, there is like lots of text about all the nuances.
Okay.
And if something is not there, not in the frequently asked questions, you can always send me an email. The email is also on the website.
Awesome. I think when you're looking at those advantages, just the shrinkage and warping that happens when you're trying to sinter a model would be valuable enough for a lot of different applications. When you look at the end part that you get, what's the accuracy that you're seeing?
Well, the accuracy that I have measured, I also have a video about it.
Okay.
It's pretty much comparable to the size of the particle of the powder.
Okay.
So if your particle is like 200, if like 100 microns, your accuracy would be about 200 microns, double that, because you have it on each side.
Right.
With the bigger parts, I do expect to have some distortion due to the thermal expansion.
Okay.
Metal and ceramic, they usually have different thermal expansion in the crucible. So you have some distortion, but it's fairly small. So I think it's one of the more accurate methods.
Okay.
Well, laser printers, they're also pretty accurate with the metal. You know what? I'm not sure. Do they compensate for the size? Well, maybe not as much, because if the part is cold, then it probably works fine for them. But they have other problem, because metal melts and solidifies 1 pixel at a time.
Yes.
Have horrible warping. So the internal stress and the part warping is pretty bad with the laser sintering.
Right. So in laser sintering systems, from what you're saying, it creates a lot of stress within the part because it's kind of sintering at a pinpoint, and that's different in your process because it's melting all at once.
Yes. So when they melt and it solidifies, it cools down, and it cools down, it shrinks. So it pulls the other parts next to it. So you end up with lots of microscopic cracks. So it's not just bad for the warping. That's why they have to add lots of support.
Yes.
To make the part not warp, which you have to manually remove after that. Here, I didn't have to remove anything. So this is the piece that I got out. Well, I polished it a little bit, but I don't have to break any supports out.
Right. You just pull it out of the sand, right?
Yes. And at least in theory, the parts should be 100% dense. Not with the vapor infill, but with a liquid infill. It should be 100% dense. With their process, it's not, because it solidifies, it cracks. There always would be microscopic cracks.
Right.
And if you just take it as is, it will not be very strong because of the cracks. There are ways they can improve it. They create this like hot isostatic pressure or something. They make it a little bit more dense, but it's still kind of complicated, and it's still not 100% dense. But this can be 100% dense. If your materials are clean, if they don't have any like dirt or impurities that would generate some voids, it should be 100% dense.
Yeah.
And it's simple.
It is very simple conceptually compared to, these machines that cost over $1 million, and they have high-powered lasers and fine optics and all of this stuff. When you look from a time standpoint, once you've printed the part in the crucible, how long, if you just take iron and copper, for example, at least that's kind of the example that I saw most often online, how long does it take for the infill metal to create your part?
Okay, so the powder it takes to deposit, well, depends on the complexity of the part, several hours.
Okay.
Some simple parts, maybe like a couple hours. Complicated ones, those were fairly complicated because the pourer had to open and close many times.
Yes.
So it was like 17 hours for 2 rooks. Then we're not printed in the same run. This one was a very old experiment. Parameters were on, so it's melted. This one was the last one. So you need to bake it just enough for the infill metal to melt.
Okay.
If you can put a lot of power and warm it up to the desired temperature instantaneously, well, it will be very fast. But I am using clay crucibles, and clay crucibles, you cannot heat them very fast. You have to heat them slowly, otherwise they crack.
Okay.
If you have a graphite crucible, yeah, you can probably heat it very fast. So again, there are so many options. Maybe eventually you would be doing it like this. You would not be even like warming up the kiln or furnace. Maybe the furnace would be running all the time. So you take your crucible, put it in, close it, and like take it up out of after like a couple minutes. Well, if your part is big, it might take longer to like warm up the whole part. But so there are many things to optimize. But in theory, you can do it pretty fast.
Yeah. I love that answer for a lot of reasons. I think the biggest one is I can relate so much to your answer. So much when people ask me questions about 3D printing, they're like, "Oh, well, can you do this?" I'm like, it depends. It depends on your material, your printing process, your overhangs, your tolerances, what's the end use goal for the part. Like there's always variables there. And the crucible thing is something that I hadn't quite thought of, but I can imagine how the crucible material and how that behaves affects heat up, cool down times when you're making metal parts. So lots of really cool nuances to think about. When you are sourcing your metal powders, I know that there's like a million different quality standards of metal powders. Is there like are you using MIM powder? Is it something finer or coarser than that?
Coarser. So there is a big challenge for the powders, because most of the powders that are manufactured today, they are for different printers. They're either for laser printers or for MIM, and in most cases they're too fine. They're too small. And in case of MIM powders, they're usually water atomized, which is not good. Because if you, let's say, water atomize iron powder, it would be somewhat oxidized, and it would contain lots of hydrogen. Because iron has higher affinity to water, to oxygen, than hydrogen. So it would absorb lots of hydrogen, and you end up with lots of bubbles in your part. So iron powder is like tricky to find. We have found a good copper powder. So now we have a good amount of good copper powder. And we had a little bit of nickel powder, but it was fairly expensive and not quite as good. So powders are tricky. Eventually, if this will be like more or less mainstream, well, there will be many manufacturers who manufacture the powder specifically for this, and they will be much better and cheaper.
Right, that makes a lot of sense. You mentioned iron and copper and nickel. What materials have you worked with? So you also mentioned glass and ceramic. What materials have you worked with so far, and are some of them easier to work with than others?
Yes. So I think the easiest to work with would be bronze. Copper and tin. The tricky thing about brass, like this, is that zinc oxidizes a lot. So it's very hard to print it with a traditional liquid infill metal. So I can go into details, but maybe for some other video. Bronze is easy. Relatively. So here is like a general problem. So far, we have been doing experiments mostly with carbon atmosphere. So you place a piece of coke or several pieces of coke powder in the crucible and close it. So it's enclosed. When you warm it up, carbon coke is carbon. Carbon starts to oxidize, and it produces carbon monoxide and carbon dioxide.
Okay.
And the ratio of the carbon monoxide to carbon dioxide would be determined by the Boudouard reaction. So you have this equilibrium, and this equilibrium changes with the temperature.
Okay.
But the problem is that this reaction goes both ways all the time. So you convert between carbon and carbon dioxide to monoxide, and the other way around. So what's happening? You're taking carbon, solid carbon, making into gas, and then back into carbon. The problem is when you convert it back to like solid state, it converts back to carbon, it precipitates as a soot.
Okay.
Not necessarily in the same place where it evaporated, not evaporated, but in the same place where it's originated.
Sure.
So the longer you bake, the more soot you'll have on your powder.
Okay.
So if you warm it up very, very fast, then it will be probably okay. But if you like take your time and do it slow, then you'd have some good amount of carbon, and your part would contain lots of carbon.
Gotcha.
And if you contain like way too much carbon, it might not even infill, because graphite would not be wettable by the molten metal.
Right.
And with the stainless steel crucibles, they expand.
Okay.
So you get distortions. So I had some videos when you like measure some distortions. Clay doesn't expand that much, but you cannot warm it up too quickly. So carbon is easy, but it's tricky to get a high quality part. You can get an okay quality part, but if you want to get a like space quality part, it's tricky. And right now we are aiming for the space quality parts.
Okay.
So if you want to get really high quality parts, it's better to use hydrogen instead of carbon.
Okay.
Because hydrogen does not have this Boudouard reaction when it transfers to solid and gaseous. It's always gaseous.
Right.
So it doesn't mess up the chemistry of the part.
Okay.
You might get some hydrogen absorbed into your print, but it's fairly easy to get it out. I think if you like on the way down, when you cool down the part, you like wait for a couple hours at something like 300 degrees.
Okay.
Hydrogen gets out. You can read about hydrogen embrittlement. So basically, hydrogen is a much better in theory. In practice, it's harder to get a hydrogen furnace than a regular kiln.
Gotcha.
So we've got recently a hydrogen furnace, but we have not tried it yet.
Okay.
One of the concerns is the safety. If you try to buy a hydrogen furnace, it's insanely expensive.
Okay.
And the reason it's insanely expensive is that the regulations are very strict.
Okay.
I have read the regulations about how to like run a hydrogen furnace, what it should be like. And it looks like it was written with one purpose: to forbid any use of hydrogen furnaces in the United States.
Gotcha. Okay.
I don't think you need that many layers of security. You can like maybe what like I'll do. Like I would not have any of those.
Yeah.
I hope they'll not come. I hope FBI will not come. I'll run it in a place in a where it's if it explodes, it's okay. So I will be away from it.
There you go.
But there are other ways around it. You don't need to run it with a 100% hydrogen.
Okay.
You can have something like 3% hydrogen and 97% argon.
Okay.
In which case, it would be not even like it would be below the lower ignition limit.
Right.
Ignition limit. So, and maybe we can figure out how to like make a furnace secure enough to run it so it wouldn't explode. I'm not sure if it would like pass the American security standards, but if American standards are so strict, we can do it in another country.
That's true. That's true. So much of what you're saying is resonating with me. I have a light chemical engineering background. I switched partway through to mechanical and have been much happier with it.
Mhm.
But there's a part of me that still loves all of that nuance of reactions and how it works with the metals. It's
Mhm.
really cool.
Yep.
Um, Taking a step back from some of the more technical elements, um, is this a solo project for you? Do you have
No.
a set of team members? What does the company look like?
Yeah, there are several people with whom I'm working on.
Okay.
Recently, we have formed a new company
Okay.
called Atom Well. Link is on the website.
Okay.
So the idea for Atom Well is first to sell consumables. We already sell copper powder.
Okay.
So we bought like a ton of it because they didn't sell in smaller quantities. Like we asked them like, hey, can you send a little bit? Say, well, no.
Yeah.
But so we had to buy a ton, and well, I didn't do it personally, other people did it. So they filtered it to the right size and packaged it. So now you can buy it from the website.
Okay.
The other idea of Atom Well is to provide a 3D printing service.
Okay.
Once we figure out all the metallurgy, actually there are several, you asked me about metals and I kind of like didn't answer it. So there are several metals that look very promising.
Okay.
Aluminum bronze and nickel aluminum bronze, titanium aluminide, maybe nickel aluminide. So on Wikipedia, it says it's like 3 or 5 times stronger than stainless steel.
Okay. That sounds very
One of the,
promising.
yeah, one of the disadvantages of this metal, it's very hard to process.
Okay.
So if you want to like machine something out of this metal, it would be pretty hard.
Yeah.
But we don't care. We can 3D print it. We don't need to machine it that much. Maybe you can just polish some surface, but that's about it. Or like you can add a thread, something. So yeah, there are many metals you can look into. I looked probably at more than 10.
Okay.
Well, I looked more like probably close to like 50, but 10 look better than others. So what was the question that I went back to metals from?
No, actually, I really appreciate you remembering to go more in depth with the last question. I should have noticed that too. But regardless, what does the team look like
Yeah.
today?
Okay. So there are several people. I can talk about myself. I don't feel comfortable talking about them because I don't know how much they would want to share
Sure.
from their personal life. So, I started talking about the company that I'm well. So,
Yeah.
one of the ideas is to provide a 3D printing service. Another idea is to make a franchise. So, like you can
Okay.
buy a printer and tell us, hey, I want to be a franchisee. And we're going to make a website where users would be able to come and upload their models, and the website would tell them like how much it would cost, or maybe it would get several quotes from different customers.
Okay.
Not customers, franchisees. So
Yeah.
like someone is in America, he'll charge that much. Someone is in India, he'll charge that much. So there will be like a market. So the idea is to be like a platform.
Okay.
And sometimes, like if you live in another country, you might choose some franchisee that's close to you.
Hmm. I really like that idea, and I think a couple companies have done something similar. There's
Mhm.
just there's not a lot of options for printed metal, especially printed metal services where someone might not want to deal with the powder handling and the sintering
Mhm.
or the kiln firing and all that.
Yeah, actually, when you talk about the powders, traditional powders, I saw the powders for the laser printers. You have to like be in a mask because
Yeah.
the particles are so small, they get airborne very easily. So you can
Okay.
breathe them, and that's not good. Our particles are big, so they don't get airborne. Like I'll give you an example. If you like go to a desert, you'd have a sand.
Right.
So we use sand from the desert, and we remove the small particles. So
Okay.
our sand is less the airborne than the sand in the desert.
Gotcha.
So it's pretty safe.
That's no, that's another huge advantage that I guess
Mhm.
I was assuming you would still need all of the safety
Nope,
requirements just
nope,
because it's a powdered metal.
nope.
But that makes it so much more, I'm gonna say, shop friendly or
Mhm.
garage friendly
Yes.
when you don't have to worry about
Mhm.
inhaling the metal powders.
Yep.
Um, so that's definitely something that if anyone's watching or listening, they should take as a huge benefit, not
Yep.
having to invest in all of the safety environment. I know we're coming up towards the end of our time, so I like to end with some higher level questions. When you personally look at the world of 3D printing and kind of your journey with it since 2015, what's one thing that you don't like about it?
Mhm. Okay, actually, let me make one correction. The idea that I had for this process was in 2016. That's when I
Okay.
formed the company. What I don't like about 3D printing, that's a little bit of a strange question. There is nothing I don't like about the 3D printing per se. But there are some advantages and there are some disadvantages.
Okay.
So if you see some disadvantage, that's an opportunity.
Gotcha. I really like that answer actually. And the question is meant to be intentionally vague.
Okay.
So it's meant to kind of like make you think, and I've gotten answers all over the board. So there's no wrong answer there. Um, a similar kind of vague question is outside of your technology, your products, what's one thing that you're excited about and that you want to see more of? So this could be a particular trend, a particular technology, or just something that, like I said, you want to see more of.
That's a tricky question. I do like how much the plastic printers have improved.
Okay.
Like the 3D printer I bought like a year ago is much better than the one I bought in 2014.
Okay.
So I do like the trend that it's like it's all developing. So it's a new technology, it's developing. There are many companies. Some of them see me as competitor, and then they don't want to talk to me. They don't want to share. I'm okay. So if like company that has another process wants to talk to me, I can tell about everything about like I know about this process. I don't like try to keep it secret. I am trying to make it affordable. So right now the printer is fairly expensive because it takes me a long time to make one.
Okay.
But fundamentally, it's cheaper than, well, it can be cheaper than the plastic one because plastic one has this like tricky hot plastic extruder. This one fundamentally might be even simpler. You don't need to have any hot parts. So maybe in some time in the future, this printer would be about as cheap as the plastic ones.
That's so hard for me to wrap my head around, but I can see it. You're right. Like the function of the printer is fundamentally simpler than what a lot of us are using at our desks now. So in theory, we could get there.
Mhm.
Thank you so much for joining us. I'm sorry, did you have any closing thoughts?
Yes, just one like thought, maybe sideways a little bit. When they started with the plastic printers, first like DIY printers have a problem to find a filament. Nobody was making the
Yes.
filament. Only the companies that were making the filament were very expensive.
Hmm.
So now we have the similar situation with the powders, but eventually I think it will be all cheap.
That's so true. Um, Initially people were using welding rod, and then now you
Mhm.
can buy filament on Amazon. And
Yeah.
nowadays, if you want to go buy metal powder, it's really, really hard.
Yep.
um, where can people connect with you? Where can they learn more about what you're doing, or if there's any specific actions you'd like them to take? Now's your opportunity.
Okay, so I'm very easy to reach. So I reply to most of the emails, even some that are like not very good. The email is on the website.
Okay.
I'm looking for collaborators. So if you want to do a collaboration on the research, you're very welcome. I'm really open. So yeah, please reach out.
Awesome. Audience, I hope you will take him up on that offer to collaborate and help take 3D printing to the next level. I will make sure to link to all of the things that have been mentioned in this episode in the descriptions. And as always, you can find video and audio versions of all the episodes on 3dprintauthority.com. Sergey, thank you so much for joining me. Look forward to connecting in the future. Hey, you wonderful human. I know I said it already, but thank you for taking some time out of your day to listen to the podcast. I have a lot of fun making it, and I appreciate that other people might enjoy listening. If you did enjoy this episode, it would make my day if you took just 8 seconds to tap the like button and or subscribe to 3D Print Authority. That way you don't miss new episodes when they come out every single week. Happy printing.